Okay, so we're going to talk about section 6.5 now, tree diagrams. Note, actually, maybe I should say, yeah, so there are solutions for the tests from Wednesday on Brightspace if you want to take a look at that. I have no idea when the test is going to be graded, but I don't really control that. But hopefully it'll be graded soon to give you a bit of feedback. Okay, so we're going to talk about 6.5, which is tree diagrams. We've already kind of used some tree diagrams before. Remember when we were doing counting, when you have a two-step process, let's say, and let's say there's kind of three choices for first step. And 4 for the second. To visualize things, we sometimes drew these kind of diagrams which were like, you got 3 possibilities for the first step, 4 for the second, and then you could kind of see, oh, there's 12 in total, because if you add up all these things, you get 12, right? So we're going to see now another application of tree diagrams, but this time it's for probability. So let's kind of introduce this with a simple example. So let's say a bin contains 3 red cubes and 7 white cubes. Okay. And this is a very simple probability question, but it's just to get us warmed up with tree diagrams. So all we're going to do is pick 2 without replacement. Okay. And so what I'm going to do is draw a tree. So there's no question here yet, but we'll answer various questions in a minute. But I want to draw a tree diagram to sort of represent this process or this experiment. So let's say that, well, A1 is the event that the first cube is red, and let's say A2 is the event that the second cube is red. Okay. So the way you would draw a tree diagram is, so we think of like at this point here, we haven't done anything. We haven't picked any cubes. And then when we pick one cube, we either get A1, the event A1 that it's red, or you get A1 complement. Okay. And then when you pick a second cube, you either get A2 or A2 complement. And you get that in both of the different cases, right? So here you also have A2 and A2 complement. Okay. And now we're going to actually write some numbers on these branches to indicate some probabilities. So if I say, when I pick the first cube, what's the probability that it's red? Yeah? Yeah. So that we label this branch with 3 over 10, and that just means, yeah, the probability of kind of making this step from knowing nothing, right, to revealing like one red cube on the first, on the first cube, that has probability 3 over 10. And then this one has probability 7 over 10, right? So now here's a question. Suppose I'm here. So A1 has already happened. I already took out a cube and I noticed, oh, it's red. Given that, what's the probability that the next one is white? Yep. Oh, so actually, oh, sorry, red, yeah. Sorry, yeah, I said white and I meant red, and so your answer is correct. Yeah, this should be 2 over 10. Yeah, so to just rephrase that, A2 is the event that the second one is red, and so you're right, this should be 2 over 10. Or sorry, 2 over 9. Okay, so let me say that again. Okay, so this number here we got by just saying what's the probability the first one's red, which is 3 over 10. If you imagine you're here, like you've already seen the first one was red. Now for the next cube, there's only 9 cubes left, and 2 of them are red, right? Because if I already know the first one was red, I've got 9 left, 2 are red, so that should be 2 over 9. So here, basically, we label it with the probability of A2 given A1. Okay, and so this one should be 7 over 10. Or sorry, 7 over 9. Because if I've already seen one red cube, I've got 9 left, 7 of them are white, I got a 7 over 9 chance of getting white. And here we should have 3 over 9 and 6 over 9. Okay, so sorry I kind of misspoke on some of those, but this 3 over 9 comes from the probability that the second one is red given that the first one is white. So is it clear how I construct this tree? So if you then picked out a third cube, right, you'd have a third kind of column here, right? It would split into 2 possibilities, red or white, and you could label with the various other conditional probabilities. The nice thing about this tree is that suppose you have some question where you're answering part A, part B, part C, part D or something. They're asking you for a lot of different combinations of events. This can allow you to do, this allows you to compute pretty much anything you want about this experiment. So you don't have to start from scratch for every calculation. Like for example, if I want probability of A1 and A2, the way you compute this, you kind of start from the beginning and you say, okay, I want A1 to happen. That has probability 3 over 10. And then I want A2 to happen, which given A1 has probability 2 over 9. So you just kind of follow the correct branches of the tree. And the answer ends up being 3 over 10 times 2 over 9. So you just follow this branch to say A1 happened, and then that branch to say A2 happened, which is something like 1 over 15 or something. Anyway, whatever it is. Yeah. So is it clear how I came up with these numbers? Okay. And this is the same as what we've been, in some sense, this is not different from the conditional probability part of this chapter, because all I computed here was probability of A1. And here I computed probability of A2 given A1. We've already seen this formula before, that the probability of the intersection is the product of these two probabilities. This is not different from what we did before. It's just a kind of convenient kind of diagram which kind of encapsulates the experiment. Like, different, so you can get lots of different information about the experiment from this diagram. But yeah, like I said, it's not really particularly different. Let's, so how would I compute this then? So it's going to be something times something. And I want to kind of use, yep. Yep. Right? And I'm guessing you got that by just walking down the correct path in the tree diagram. We want A1 to not happen, so we go down here. We want A2 to happen, so we go up here. And you just multiply everything you see on that path. Which I guess is 7/30 or something. Okay. So now, suppose we're trying to compute probability of A2. Actually, without thinking about anything, without like computing anything with algebra, like does anyone have a feel for what's the probability the second cube is red? Like what should that be intuitively? Sorry? I think it's going to be a bit different than that. Yeah? Well, so it is going to be what you get by adding these two numbers, these two things up. That's totally correct. So actually, it would be the 3/9 as the last one but anyway, I think I see what calculation you're doing. But even without even thinking that deeply, you can kind of think, well, if I'm just like saying, what's the probability the second one is red? I mean, it's kind of the same, it should be the same as the probability the first one's red, kind of, because what's the difference between the second one and the first one? So it should be 3/10. But we can compute that formally using these two things. So the probability the second one's red is the same as the probability that they're both red, plus the probability the first one was white and the second one was red, right? Because, these are all the possibilities for the first one, so it should be A1 intersect A2 plus probability of A1 prime intersect A2, which we already computed as 1/15, and 7/30, which is 1/3, or sorry, which is, 9/30, which is 3/10. And that's exactly what I was hoping to get, right? Because it's just like picking the red one on the first time, right? If you're not sure why this is equal to those two things, right? You can draw a Venn diagram and then you see, oh, A2 is just like A2 and A1 plus A2 and A1 prime, right? It's the stuff that's in A1 plus the stuff that isn't in A1. Okay, any questions about any of that? Yeah. Well, because here we're really at the end of the day just looking at the second cube. So I kind of see what you're getting at, but here's the thing. If I pick a cube and then pick another cube, Well, if I pick them in the opposite order, it's kind of the same thing. So it's kind of picking the second cube being red is kind of the same as picking the first one being red. But it might, anyway, we don't need to get too deep into that kind of philosophy. But the point is, if I know these two things, you can compute, for example, the probability of A2 by adding them up, right? Okay. So basically, a tree diagram is super useful if you're going to have to solve a lot of problems about one experiment, because you've got a lot of information already there, and you can just multiply numbers and add them up and stuff. Yeah? It would be the same way, although that one's actually kind of easier if you think about it, because the probability the first one's red is just 3 over 10, because it's just, because there isn't we're not even thinking about the second one at that point. But you totally can solve it the same way. Okay, so let's do another example. So there are 9 apples, but 3 are poisoned. Each day, Bob eats 1 apple for breakfast. Maybe this is a bit morbid. I don't know. Yeah, it's almost Halloween. Yeah. So what? I should have saved this kind of example for later, right? Close to Halloween, but. What is the probability, and let's say, yeah, I don't know how poisonous these are, but I guess if he eats them, he dies. Let's say, what's the probability he dies on the first day, part B, the second day, and then maybe I'll add a part C later. Is it clear what we're asking here? Oh, and let's assume when he picks an apple, he picks it randomly, right? He can't tell which one's which. Yeah, maybe he just likes to play Russian roulette every day kind of thing. Oh, we could have done that example too, Russian roulette, but well. So, okay, so what's the probability he dies on the first day? This one's pretty easy. Yeah, 3 over 9 or 1 over 3 or, right? So we don't really know anything about, well, I mean, there's nothing interesting going on in the first day. It's just 3 over 9. Let's, so for part B, let's get into a bit of a tree diagram thing. So we know there's a 3 over 9 chance that, I'll just label this for D for died. This is really not that funny, I don't think. Okay. Yeah. So 6 over 9 chance of dying complement, which is, yeah, so D prime. On the second day, so here's the thing. This branch of the tree kind of ends because you can't die twice, right? So yeah, so in this case, we just kind of stop the tree. And in this case, if he doesn't die, then you've still got 3 poison apples, right? And you've got 8 in total. So you should have a 3 over 8 chance of dying on the second day, if you've survived the first day. and then a 5/8 chance of surviving. And then again, this branch terminates, and we keep going on this one. You know, and this can go on longer, but yeah, we don't necessarily, it depends how many days we want to talk about. Okay, so for dying on the second day, well, you have to survive the first day, so you have a 6/9 chance of that, right? And then a 3/8 chance of on the second day. So, wait, what is it? Which should be a quarter. Right. Okay, so who could tell me what's the chance of dying on the third day? Yeah. Sounds good to me, yep. 5/8, 3/7, right? Because again, we just follow the correct path, right? Go down here, and go up there. Which I think gives me 5/21. What about, you know, part D? Let's say that he dies after, at most, 3 days. Yeah. Yep, exactly. Right, because you just want to take, this is 1 day plus the probability of 2 days. Right, because each of these things we were computing exactly 1 day, exactly 2 days, and exactly 3 days. So you just want to add those things up. Which gives you 23/28, which is approximately, you know, 82.14%. So, okay, so it's not looking good for the first 3 days. What about if you wanted at least 4 days? So that, yeah, survives. Yeah. Yeah. Yeah, so there's going to be a really long way of doing this and a really short way of doing it, right? Because, you know, you could, in principle, you could say, what's the probability of surviving exactly 4 days, exactly 5 days, exactly 6 days, and adding all those things up. But that's going to be longer. If you think about it from part D, we already know the size of the probability of the complement, so we just take, you know, probability of at most 3, or sorry, 1 minus the probability of at most 3 days. So it's 5/28, or about 0.1786. So apologies, that's not very visible, but we just take this previous answer and we subtract it from 1, right? Because surviving at least 4 days is the opposite of dying in less than or equal to 3 days. Yep. Sorry, which one? The 1 over 4? So this was from this part B. So that the probability that he dies on the second day was 1 over 4. So yeah, this is the probability he dies on the first day, second day, third day, and we just add them all up. Any questions about that? Okay. All right, let's just keep doing examples. One more, I think, and then maybe this will be a trickier example, I think. Not that much more tricky, but so let's say Alice and Bob play 3 races of Mario Kart. And so let's say Bob, Bob goes into this really confident. He's got a 3/4 chance of winning the first race. However, every time Alice wins, she starts feeling really confident and like she has a better chance of winning the next one. So every time Alice wins, she has a 2/3 chance of winning the next race. And kind of oppositely, every time Bob wins, he gets overconfident and he like slacks off. And he only gets a 2/5 chance of winning the next race. So every time Bob wins, he has a 2/5 chance of winning the next race. Okay. A little bit complicated. Let's say this is part A. Compute the probability that Alice wins more than Bob. Okay. Is the scenario clear? It's a little bit convoluted, but okay, so to do this, I mean, you might be able to do this, well, actually, I think this would be kind of hard to just do without a diagram. I think the diagram really helps, at least for me. So yeah, let's say, so for the first round, we know that Bob has a 3/4 chance of winning. And Alice has a 1/4 chance of winning. For the second round, in this scenario, what should I write for this branch? the number? Yeah, because here we're in the situation that Bob has already won the first game, the first race. So he should have a 2/5 chance of winning the next one, because every time he wins, he gets a 2/5 chance of winning the next one. And Alice will have a 3/5 chance of winning the next one. Now let's do this bottom one. So far this is just going to be for the first two races, right? So this is kind of, I'm assuming Alice lost, Alice won the first race. She now has a 2/3 chance of winning the next one, right? Oh, sorry. I need to say what these are. So this is, so if she won, she has a 2/3 chance of winning. So if the first one was A for Alice, the next one should be 2/3 of being A again, 1/3 of being Bob. I think for me, the hardest thing here is just making sure I write this whole thing down correctly. Okay. So for these branches, this was Bob won, Bob won. So Bob has a 2/5 chance of winning. Here it was Bob won, then Alice won. Since Alice won here, I've got a 2/3 chance of Alice winning again, 1/3 for Bob. I don't know why I decided to put B's on top and A's on the bottom. I feel like that's messing me up here. Oh well. But if you think through this and you kind of double check yourself, like, yeah, you can make sure this is all correct, right? Like, for example, if I look at from here, from this A, this was Alice winning a race. It should be 1/3 to Bob, 2/3 to Alice after that, and so on, right? Okay. So now I want to get the probability that Alice wins more. And there's quite a few different ways that can happen, right? Like it could be that Alice wins all three of them, or Alice wins the first two and loses the last one, or wins the first one and the third one but loses the second one, or loses the first one and then wins the next two, right? We've got to add up over all those possibilities. Okay, so first I've got the, so I'm going to just sort of write them down. So I've got the possibility she wins every match, or every round, race, whatever. It could be Alice, Alice, and then Bob wins the last one. It could be Alice, Bob, Alice, or Bob, Alice, Alice. Right? What's the probability of it being Alice, then Alice, then Alice? Yeah. Yeah. Actually, before we continue, who thinks Alice is going to win more than Bob, more than 50, with a higher than 50% chance? And who thinks Bob's going to win more with a higher than 50% chance? Oh, interesting. It is interesting because, I mean, Bob's got a huge advantage on the first round, right? So he's probably going to win the first time. So it's not really clear which way this is going to go. Anyway, so, okay, so the second one, we've got 1/4, 2/3, right? Like, because the first two rounds are the same as the previous thing, so it should be the same probabilities here. But then last round, or last race, we're saying it's Bob, so it should be 1/3 instead of 2/3. I again have 1/4. Then we've got a 1/3 chance that Bob wins. So, okay, let me be careful for this third one. So we're doing 1/4 for Alice. We're doing A, and then B, and then A. So the last one should be 3/5. Okay. For Bob to win, that happens, for the first round, it happens most of the time. So 3/4 chance. And then we need Alice to win and Alice to win. So 3/5, 2/3. Okay. So I think if you compute these numbers, you get a 9th plus 1/18 plus 1/20 plus 3/10, which gives you a grand total of 31/60, which is a little bit more than 50%, right? So it's approximate, or it's 0.516 repeating. Okay, so even though she's probably not going to win the first round, she's got a little bit more than 50% chance of winning the whole, winning more than Bob. Any questions about any of these steps? Yeah? Yeah, like for example, that one, or? Yeah, so if we go A, and then B, so A, so like A, and then B would be Alice wins, and then once Alice wins twice, like once Alice has won, she has a 2/3 chance of winning, which means Bob has a 1/3 chance of winning. Yeah, no, that's all good. But if you draw your tree correctly, you can just compute these things really fast. But the hard part is drawing this correctly, I think. Basically, one thing to notice, like from any place on the tree, if you go to the one step to the right, these different branches, and there could be many different branches, they should add up to 1, right? So that's one way you can kind of find mistakes, right? If these don't add up to 1, you've got a problem, right? Okay. Let's do another variation here. So let's say this is part B. What's the probability that the person who wins the first race wins more races than the person who didn't win the first race? Okay, is it clear what this is asking? Okay, so one thing that's kind of counterintuitive about this is like, well, okay, we know Alice is most likely to win more races. We just computed that. But we also know Bob is more likely to win the first race than Alice is. So it's kind of like, I don't know, it's not clear, because if Bob is usually winning the first time, but Alice usually wins overall, it's not, should the person who wins the first race usually win more? It's not completely clear. So, okay, we need to first we need to figure out what are all our possibilities here. So it could be that Alice wins the first, and then she just wins everything, right? That's one possibility for the first, for her winning more. For the person winning the first one to win more. It could be that Alice wins the first one, wins the second one, and then loses. Wins, loses, wins. Right? And I think these are all the possibilities that we should be counting where Alice wins first, right? Because there's no other way for her to win first and win more races. And then you've got the kind of opposite things. So you just change the A's to B's. Okay. So 6 possibilities in total. Here I've got a quarter, 2/3, 2/3, a quarter, 2/3, 1/3. So these are the same as in the previous one. Actually, the third one's from the same as in the previous two. So it's quarter, 1/3, 3/5. Probability BBB is 3/4, 2/5, 2/5, right? Because it's, follow the top thing. Then we've got three-quarters, 2/5, 3/5. Then we've got 3/4, should be 3/5. And now Alice has 1, so 1/3. Okay. You can see these calculations get pretty long, but not much we can do about that. So 1/9 plus 1/18, 1/20, 3/25. I don't think I computed all of these. Anyway, I think at the end of the day, you add these all up. You get 2/3. So 2/3 of the time, the person who wins the first race wins more races than the other person. Does that make sense? Or is it clear how I came up with these 6 possibilities? So that's one thing you've got to be good at. You can't miss any possibility here, right? Okay, now let me tell you that actually the way I computed this wasn't that smart. There was a smarter way to do it. You should kind of think, so out of all the different things here, like there's 8 different possible outcomes, right? Because each race can be Alice or Bob. There's 3 races, so there's 8 possible outcomes. And here I added up 6 of them, which seems a bit silly because I could just take the ones that I shouldn't count and subtract them, and that would be faster. So let me just say this is 1 minus the probability that, so the ones we don't want to count are where the first person who wins doesn't win the most. So that could be like A and then BB. or it could be BAA. So you can, hopefully you can see that if I did it this way, it'd make life a lot easier, right? So a quarter, a third, 2/5, 3/4, 3/5, 2/3. And if you do the calculation, I'm pretty sure you get 2/3. Okay. So is it clear why this is, this is the same, computing the same thing as that one? We take the whole 100% probability and subtract the ones we don't want to count.